Hi, I'm Nick Tenerelli, and today I'm going to talk about rings. And start with the brief outline of what's going to go on here. First, I'm going to talk about the properties of rings, then go into subrings and commutative rings. And you'll be able to see that these are very similar to groups, subgroups, and abelian groups, which we've learned about prior to this. Then I'll go into zero divisors and units, which are important as we move forward with rings, as we go into fields, and also with isomorphisms. Those things will become important. And then I'll finish up by talking about a specific type of ring called a polynomial ring. So let's begin with the definition. So a ring is defined as a set R with binary operations. We'll call them plus and multiplication that satisfy the following properties. Let's start, before I get into those, let's talk about the plus and multiplication. Those can be any operation. I'm just calling them the additive and multiplicative operations just for simplicity's sake, but they really could be anything as long as they satisfy these properties. R, the set has to be an abelian group under addition, which we've learned about prior. R has to be closed under addition, it has to be associative, commutative, and has the additive identity 0, as well as every additive inverse has to be in R. It also has to be closed and associative under multiplication, and it has to distribute like so. So A times the quantity B plus C has to equal A times B plus A times C, and it has to work on both sides. So it can't just be a left side distributed, it has to be both left and right sided. A subring, the definition is if we have R1 and R2, where R1 is a subset of R2, and R1 and R2 are both rings with the same operations, then R1 is a subring of R2. As you can tell, this is the exact same definition of subgroup. If you just replace every word ring with group, it translates the same way. Commutative rings. This is where multiplication is commutative. This is what is known as an abelian group if it was just a group. So just A times B has to be the same as B times A. If we take the real numbers, which you guys are all familiar working with, and you just say, let's say 2 times 3 is the same as 3 times 2, they both equal 6. You can do that with any real number, and it will work. So that means that the real numbers under multiplication and addition is a commutative ring. A non-example here is M2R. That's just a set of 2 by 2 matrices with real numbers. That's what the R denotes there. So let's take a look at this. This is a non-example because this is not a commutative ring. However, it is a ring, it's just not commutative. So if you did the first, the blue matrix 0, 0, 0, 1 multiplied by 0, 1, 0, 1, you end up getting 0, 0, 0, 1. But if you switch the order around, the output is different, and that doesn't work in a commutative ring. Therefore, this is not a commutative ring because these elements are not commutative. Let's move on to another example, and this is an example you guys all should be familiar with as well. Z6 under addition and multiplication, and this is just the integers under mod 6 addition and multiplication. So if we pull out the Cayley table for this, for multiplication, we get this, and a few interesting things pop up. First of which is this whole first row of zeros, which you don't see in the addition Cayley table because every element is in each row, or pretty much actually every element is in each row. But since 0 times anything is 0, that just becomes 0. So it's kind of interesting, but more interesting comes in the middle here. So we have 2 sections here where the zeros pop up, as you'll see here. And this comes really interesting because we get zero divisors. And this is where any 2 elements, when multiplied together, and neither of those 2 elements are 0, they equal 0. So as you can see with the definition here, our 2 elements here, let's just choose 2, 2 and 3. 2 times 3 end up equaling 0 under mod 6 multiplication. The other 2 elements there, 3 and 4, are also, where it goes equal 12, and 12 also equals 0 under mod 6 addition. Another example we have we could use Z4. All right, 2 times 2 equals 4, and that equals 0 in mod 4 addition. So we can kind of generalize this, I guess you can say, where Zn, where n is even, those will always have be have group, sorry, be rings where that contains 0 divisors, because anything, there'll be an element in there times 2 that ends up getting back to n, which will equal 0. And then we can take this another step forward, and even more general, where Zn, where n is not prime. So Z7 will not be 0 divisors, but Z9 will, because 3 and 3. Z50 will, and so on and so forth. And as long as n is not prime, there will be 0 divisors in that ring. The alternative to, well, one of the alternatives to 0 divisors, and another special type of element, is called a unit. A unit in a ring is any element that has a multiplicative inverse element. So as long as A times B equals 1, where both A and B are in that ring R, then those two elements are called units. 1 is a special type of unit, it's called unity. And it's kind of a, certain people describe 1 as the unit, some people describe it as unity, so it's a little confusing at times. But we're going to refer to any element with a multiplicative inverse as a unit and 1 as unity. So if we go back to that Z6, we'll see in the Cayley table there are 2 here that have that unit. So 1, obviously since it's unity, 1 times 1 always equals 1, no matter what ring you're in. 1 times 1 will always be 1. It's always a multiplicative identity times unity. But 5 times 5 here equals 1, because 5 times 5 equals 25, which mod 6 addition equals 1. So we have 2 units here. And like I said before, these are important in terms of 0 divisors are important in terms of field. Units are really important when trying to map isomorphisms, because units must map to units, 0 divisors must map to 0 divisors. So now let's move on to polynomial rings. And if R is a commutative ring, and Rx, the ring Rx equals P of x, where P of x is an expression in the form of A0 plus A1x plus A2x is 2 plus so on, an x to the n, where AI is, where each coefficient A is a real number and the power of the x is greater than or equal to 0. So example of that, just P of x and Q of x here. So it's going to be P0 plus P1 times x plus P2 times x to the 2, and Q of x is Q0 plus Q1 times x, so on and so forth, all the way down. The way you add these is by grouping the coefficients together. So anything with x to the power of 0, the coefficients of those will add. So P0 and Q0 will add together. P1 and Q1 will add together. Pn, Qn will add together, because you group the ones that are multiplied together by the same x power, I guess you can say. Multiplying these together, it's a little more complicated as a general formula. So it's P times Q will equal S0 plus S1x plus S2x squared all the way to Sn times Xn, where each Si equals P0 times Qi plus P1 times Qi minus 1 all the way through to Pi times Q0. And that's just, if you were to multiply it out by hand, it would just be each coefficient, everything that ends up being involved with the same power of x, which makes sense because that's how you want them to be together in the end. The degree of a polynomial is another property that you could characterize a polynomial by. It's it's if P of x is P0 or P0 plus P1x all the way through Pn Xen in the ring, where Pn is not 0, then the degree of P of x is n. It's the highest numbered exponent on x. So if you look at my example here, we have 2 plus 3x minus 5x cubed plus 7x to the fifth. The degree of that will be 5 because it's the highest ranked exponent. It's not 2 because that's the first number, and that wouldn't make sense because this is a commutative range, so you could just switch around the numbers anyways. It's not 7 because that's the coefficient for the highest ranking polynomial, but it's actually the number in the highest degree, or the highest numbered polynomial. And this bottom example, q of x, where it equals -1 plus x squared plus 0x cubed, the degree of that polynomial is 2, because this is 0. So it's the leading coefficient. 0, it goes away. So x squared is the one that stays. Next property we could talk about is being irreducible. Polynomial is irreducible over f if there are no polynomials q of x and r of x in that field, polynomials of degree greater than 1, such that p of x equals q of x times r of x. So an example of being reducible is x squared minus 1, because you can break that down into two different polynomials. When they multiply together, they equal x squared minus 1. And this is a simple one that you guys are familiar with, so x plus 1 times x minus 1 will get you there. An example of being irreducible is if p of x were to equal x squared plus 4, because you can't break that down into anything with real solutions. However, it is technically still reducible, it's just not reducible with the real numbers. If over the complex plane, or complex, the field of complex numbers, you can break that, you can reduce that into x plus 2i and x minus 2i, and therefore you can reduce it. However, if the field fx is over the real numbers, then this is an irreducible polynomial. So to review, went over the properties, definitions of rings, its subrings, commutative rings, which are, like I said, similar groups. Then we talked about specific elements of the ring called zero divisors and units, which will be used in the future. And then we talked about specific ring of polynomial rings.